So I want to welcome you to part 2 of lecture 2. This is complex numbers and quadratic equations. My name is Jorge. And this is for college algebra. Now, the objectives for this particular lesson is going to develop an understanding of the imaginary unit I in complex numbers. We're going to perform operations with complex numbers, and then we're going to write the results in standard form. We're going to find a complex conjugate of a complex number, and then we're going to go ahead and solve quadratic equations that has a complex solution or solutions. So the first thing is the imaginary unit. I squared is equal to -1. Now, complex numbers are numbers in the form of a plus bi, where a and b are real numbers. Now, the real number a is called the real part of a plus bi, and the real number b is called the imaginary part of a plus bi. Now, I want to talk about equality of complex numbers. So a plus bi is equal to c plus di if and only if a is equal to c and b is equal to d. Now, the next thing is the sum and the difference of complex numbers. So how do we add complex numbers? So if we have a plus bi plus c plus di, that's going to be equal to a plus c, so we add the real part, and then plus b plus d, so we add the imaginary part. The difference is if we have a plus bi minus c plus di, we subtract the real parts and then we subtract the imaginary parts. So here we have an example. We have 3 minus 2i plus 5 minus 4i, and then we have the same values but subtracting. So the first thing is that we add the real parts. We do 3 plus 5, and then we do -2 plus -4. So then we end up with 8 minus 6i. So the sum of 3 minus 2i and 5 minus 4i is 8 minus 6i. So now in part B, we have the difference. And so again, we subtract the real part and the imaginary part, and then we end up with -2 plus 2i. The next thing that we're going to talk about is multiplying complex numbers. So here we have 3 minus 2i and then times 5 minus 4i. So the way that we do this is the way that we FOIL when we're multiplying binomials. So we do 3 times 5, 3 times -4i, -2i times 5, and then -2i times -4i. So then we end up with, when we carry this out, we end up with 15 minus 12i minus 10i plus 8i squared. Now, remember that at the beginning I told you that I squared is equal to -1, so we can go ahead and rewrite that I squared as -1. Now, -12i minus 10i is simply -22i. So now we have 15 minus 8, so we end up with 7 minus 22i. So the product of complex numbers, here we have the step-by-step. So then now we have a theorem. The product of a complex number and its conjugate is a non-negative real number. So that is, let's say that z is equal to a plus bi. Then z times its complex conjugate is equal to a squared plus b squared. And so conjugate. So if z is equal to a plus bi is a complex number, then its conjugate, denoted by z bar, is defined as z bar is equal to the conjugate of a plus bi, which is a minus bi. So multiplying a complex number by its conjugate. So if the complex number is equal, z is equal to 3 minus 2i, then its complex conjugate, z bar, is equal to 3 plus 2i. So if we multiply those two together, we get 3 minus 2i times 3 plus 2i, which is going to give us 9 plus 6i minus 6i minus 4i squared. And the two middle terms are going to cancel out. The I squared is equal to -1, so we end up with 9 plus 4, which is 13. So the next thing we're going to do is write the reciprocal of a complex number in standard form. So we're going to write 1 over 3 minus 2i in standard form of a plus bi. So that is, we're going to find the reciprocal of 3 minus 2i. So here we have 1 over 3 minus 2i times 3 plus 2i divided by 3 plus 2i. So if we multiply that out, we end up with 3 plus 2i over 9 plus 4. Remember, if I multiply a complex number times its complex conjugate, I get a real number. So that's how we end up with 9 plus 4. And then we end up with 3 plus 2i over 13, and then we have to write that in standard form. So the a part is 3 over 13, and the b part is 2 over 13. So here we have a complex number. So we have 3 minus 2i divided by 5 minus 4i. So we're going to write this in standard form. So the first thing that I do is I multiply by the complex conjugate of the denominator, which is 5 plus 4i. So I go ahead and FOIL that out. Again, the denominator is going to be a real number. My numerator ends up being 15. It's going to end up being 15 plus 8. So I end up with 23 plus 2i over 41. And then in standard form becomes 23 over 41 plus 2 over 41i. So here we have some more examples. So let's say that z is 3 minus I and w is 2 minus 5i. I'm going to write each one in standard form. So z over w simply becomes 3 minus I over 2 minus 5i. We multiply by the complex conjugate of the denominator, and then we multiply it all out. So we end up with 11 over 29 plus 13 over 29. Remember, you're going to FOIL the numerator and the denominator. So we're going to end up finding the conjugate of z plus w. So we end up with the conjugate of 3 minus I plus 2 minus I minus 5i, which is the conjugate of 5 minus 6i, which is 5 plus 6i. And then the last example is z plus this complex conjugate. So 3 minus I plus 3 plus I, and that's just going to give us 6. So the conjugate of the sum of two complex numbers equals the sum of the conjugates. We can divide that up, and the conjugate of a product of complex numbers equals the product of the conjugates. Now, theorem, the conjugate of a real number is the real number itself. Another theorem, the conjugate of a complex number is the complex number itself. The conjugate of a sum of two complex numbers equals the sum of their conjugates, and then the conjugate of the product of two complex numbers is equal to the product of their conjugates. So here we're going to talk about the powers of I. So there's a pattern here. So I to the first power is I squared is negative 1, I to the third is just negative I to the fourth is 1, and then I to the fifth is I to the sixth is negative 1, I to the seventh is negative and I to the eighth is 1. So you can see that there's a pattern. So the powers of I repeat with every fourth power. So I to the 33rd power is just equal to I to the 32nd times I, which is simply just I to the fourth raised to the eighth, which is just 1 to the 8th power times I, which is just I. I to the 82nd power is I to the 80th times I to the second power. We further reduce it some more, and then we end up with negative 1. The next thing is we're going to write the power of a complex number in standard form. So we're going to write 3 minus 2i to the third power in standard form. So we're going to go ahead and use a special product formula that x plus a to the third power is just equal to x squared plus 3ax squared plus 3a squared x plus a to the third. So therefore 3 minus 2i to the third power is going to be equal to the following. Now in this case x is 3 and a is negative 2i. So we go ahead and just substitute that in the formula here in the middle. And then we simplify, and then we end up with negative 9 minus 46i. Now, if n is a positive real number, we define the principal square root of negative n, denoted by the square root of negative n, as the square root of n times I. So the square root of negative 1 is equal to the square root of 1 times I, which is just I. Square root of negative 9 is the square root of 9 times I, which is 3i, and then the square root of negative 18 is the square root of 18 times I, which is 3 square roots of 2i. So the next thing we're going to do is we're going to go ahead and solve some quadratic equations in the complex number system. So here we have x squared equals 9. So, so let's do this. So what we do now is we square both sides. So again, we end up with x is equal to plus or minus square root of 9, which is x is plus or minus 3. Now the next one is x squared plus 25 equals 0. So, So we have x is equal to plus or minus square root of negative 25, which becomes the x is equal to the square root of the square root of 25 plus times I, which is plus or minus 5i. So here's another theorem. In the complex number system, the solutions of a quadratic equation, ax squared plus bx plus c equals 0, where a, b, and c are real numbers, and a does not equal 0, are given by the following. X is equal to negative b plus or minus square root of b squared minus 4ac over 2a. So we're going to go ahead and solve the equation x squared minus 6a plus 13 in the complex number system. So here we have the discriminant. Discriminant is negative 16. So that means that there are no real solutions here. So we plug these values into our formula, and we get that x is equal to 6 plus or minus square root of 16I over 2. We further simplify that to 6 plus or minus 4I over 2, which then becomes 3 plus or minus 2I. So again, this is from the previous lecture, so you can go ahead and just kind of look at that. So let's go ahead and, without solving it, determine the character, the solutions of each equation. So this is equal to 1, so there's two unequal real numbers. The second one, we get negative 76 for the discriminant, so therefore the solutions are two non-real complex numbers that are conjugates of each other. And then the last one is equal to 0, so this is a repeated real number, it's what we call a double root. And that's the end of lecture 2. Thank you.